Okay, so the first thing we're doing is, so today we're gonna jump back and forth a little bit. We're starting on the beginning of chapter 23, which is, so it's 20, we're about to do 23.1 to 23.4. I think. Then we're going to 9. Then we're going to 23.5. And then to 23.6. You don't have to write this down. I'm just trying to show you what we're doing right now. We're kind of, because we need to go back to 9 before we talk about the end of 25. Basically, the reason we're going back to 9 is it's on multiple regression, which is multiple predictors, which is just a conceptual step up. But first, you see the table right there. We're going to be talking about the regression, your 9th hypothesis test, your regression test. Yeah. Yes. So just a quick recap. This was from chapters. I definitely recommend rereading chapters 7 and 8 because it's been a while. But we have a bunch of data, and we want to fit a line to it. That's the basis of linear regression, right? We have linear data. We want to put a line to it because it's much easier to interpret lines than just random points. And of course, we try to minimize the residuals. So, reminder, residual is, we call it E. It is y minus y hat, which is the observed minus the predicted. So like if this is a data point, this red line indicates the residual. It's a distance. It's a vertical distance, whether positive or negative. You might remember the residual plot. And do you guys remember from test 1 what you want this to look like in words? You want it to look patternless and evenly spread above and below 0. Basically just a bunch of random points. Is the residual plot. So what have we been doing so far, right? Hypothesis tests, we assume something to be true, we're trying to prove it's false. So in this, we assume this is beta, the Greek letter beta. Beta is the true slope. This is your parameter for regression. We assume the true slope of our regression line is 0. What does that mean practically? That means there's no relationship between x and y, right? Bless you. That gives you a line that just looks like this. There's no information that you get from that, right? That's just y equals, 5 or whatever. There's no, so basically the null hypothesis in English basically means we can't do regression. That's what the null is. The alternative, there's only one alternative. It is beta is not 0. This is in English saying we can do regression. Any questions on that? It's patternless and evenly spread above and below 0. This is also called it's the equal variance assumption, which we're going to talk about again in yeah. No, that's a good point. This just represents the true slope of the line. So yes, that is a little confusing. You can do beta 1 because if you guys remember, I have all this stuff over here. I gotta move this over. The equation regression line is y is b0 plus b1x. So beta, you could do beta 1. So beta 1 is the true slope. I think on did I do beta over here? Yeah. But yeah, if you want to put the subscript 1 to not confuse yourself, go for it. So we need parameters. You always need a sample size. You need your B1, which is your sample slope. You need S sub E. This is not standard error. It's standard deviation of the residuals. I'll write out what the equation is for that in just a minute. And then you have S sub x. This is your standard deviation of the data. That's the square root of the sum of xi minus x bar squared over n minus 1. No, these are not proportions. This is actually going to end up being a one sample t-test, just with a different context. So technically B1 is a mean and beta is a mean. But these are the 4 parameters you need. All right, it's all cramped. I gotta move this over. So S sub e, that's a lowercase s with a subscript lowercase e, is the square root. This is not Xing out. Come on. It is the sum of residuals squared over n minus 2. The square root is over the entire thing. You can also use the definition of the residual up here, like the sum equals 1 to n, yi minus y hat squared over n minus 2. We're going to talk about why the denominator is n minus 2 in just a second. But the fact that it's n minus 2 is very important because your degrees of freedom are going to be n minus 2 for this. So Sx is your standard deviation formula. All right, everyone remember this? For people who weren't office hours, how many variables are in the bottom formula? Okay. Yeah, I already told you this. There's one variable in here, which is x, right? N is a number. X bar is a function of the x's, right? It depends on what your data is. There's one variable. So in SE, there's 2 variables. Because remember, y hat is b naught plus b1 x. Basically, y hat is a function of x. So in SE, it's dependence on 2 variables, x and y. You guys see that? That's why it's n minus 2 degree on the bottom instead of n minus 1. What? No, because it's just a number. For each problem, it's fixed, right? Because you're gonna know how many data points there are. Yeah. Yeah, n is always sample size. Yeah. This is just some intuition behind why it's n minus 2. So now I'm gonna write the assumptions over here. There are 4 assumptions. The first is the straight enough condition. This just means we have data that look like we can fit a line to it. You know, whether it's upward or downward sloping. 2 is, well, randomization condition, you know, random sample. That's the easy one. 3, the equal variance assumption. Also known as the does the plot thicken condition. I definitely recommend rereading chapters 7 and 8 before you do the homework, because the homework for next week's going to be on this stuff. There is going to be stuff in chapter 25, but that won't be graded. You should do it though, because the ANOVA stuff for next week is going to be like heavily represented on the final, like disproportionately. So definitely do those problems too. But definitely reread chapter 7 and 8. what we want this to look like is the good residual plot. We don't want there to be patterns, right? This is bad. Something that has this like fan shape is bad. Or something like this is bad. But this is good. And you'll need to see the picture in order to, like, you'll have this picture on your test. Any questions so far? One more condition. Fourth is the normal population assumption. This one has two parts. The first is the nearly normal condition. It has a slightly different meaning. It is the histogram of the residuals. Has to be unimodal and symmetric. Two is the no outliers condition. And you need to look at the normal probability plot, which will be given to you. It should look something like that. You know, you don't want outliers. But it looks kind of like a straight line, and there might be like some tails. Tails are okay, but something like this red point is bad. Those are the four conditions. Any questions on those? Just really, so, you know, you're going to need to see a scatter plot, a residual plot, a histogram, and a normal probability plot, and see the words random sample. So those are the five things. Not a full one, no. Oh, it's gonna be a few different things. Because this is only like one of the kind of 2.5 topics we're talking about today. Yeah. So then we have the math. The standard error of the slope is the standard deviation of the residuals divided by the standard deviation data times square root n minus 1. B1, yeah. Standard error of the sample slope is standard deviation of the residuals divided by standard deviation of the data times square root n minus 1. It's a little different than your previous standard error formulas. Yeah, B1 is sample slope. Yeah. Yeah. Standard deviation of residuals. And SX is standard deviation of the data, the X data. And then obviously n minus 1 is sample size minus 1. Yeah. Okay. One more step, the t-score. So it's t with n minus 2 degrees of freedom is B1 minus, we'll talk about that in a second. What is our assumed value for the slope? 0, because we assume beta is 0. So you don't have to write the minus 0. I just want to show it to you. But it's basically the sample slope over the standard deviation. You can exclude the minus 0. And then you find your p-value by going on the t-table. You conclude, you know, reject or fail to reject. And that's the hypothesis test. So it's a one sample t-test with a different context. And let me show you why it is a t-test. So you have a scatter plot. For a given value of x, you take a sample, you get a value, bless you. You take another sample, you get a different value. You keep doing this over and over again. You get a sampling distribution. And what this resembles by central limit theorem is a normal curve. You know, just turn your head sideways. You go to another value. First sample, second sample, third sample. You keep sampling. You get another normal curve. And you do this for every point of X. Then, how do you make a regression line? Well, you go through the center. Through the means of the normal curves. Now, so the variability in Y is a t distribution that approaches a normal if you have a big enough sample size. So if all of these means are level with each other, if they all equal the same thing, then the slope is 0. That's your null hypothesis. That they all have the same means, so the slope is 0. Your alternative is basically saying, you know, it either goes up or it goes down. So you have a slope. But the point is the variability resembles the t distribution. And that's why we use a t-score. Any questions on that? Because that's kind of complicated. Now, the big thing that this hypothesis test is lacking is, let's say you reject the null hypothesis. The next question is, okay, like, is our slope positive? Is it negative? So we use confidence intervals for that. And the confidence interval formula is your sample slope plus minus t critical with n minus 2 degrees of freedom times your standard error. Which this formula should make, it should make sense because it's your estimate plus minus your critical value times your standard error. And then that gives you a sense for where, where your slope is going to be. And that's your regression hypothesis test, your 9th hypothesis test. 9 out of 10. Confidence interval. Yep. Any questions so far? Okay. So, did I take one of these questions? No. Where's the book? Okay, right here, number 13. This is an example of what you'll see on your final. Kind of. You'll see this table. And knowing how to interpret this table is very important. So actually, that's 2 variable. Never mind. This one's better. Get rid of that. Okay. So first of all, this residual plot, does that satisfy the equal variance assumption? Doesn't look too bad. I'd say overall it's okay. You might want to be a little careful with the outliers. Here's the other thing though. Well, yeah, it is a little skewed up. Generally, like overall, it's okay-ish. This would, so this is what it looked like, right? A positive, E is y minus y hat. So positive residual means your data is much above the line. So if this is your line, you'd have, you have the points below, but you would have some high points. That it could definitely be an issue. If the chart ended around there and anything above it wasn't there, then it'd be perfect. But there's definitely some cause for concern now. Okay. Hey, focus on the table part. What is our intercept? What variable is the intercept? This is not a trick question. Say it out loud. Which variable is the intercept? Intercept, right? Which one is our slope? SAT score. So what would the equation of our line be? I'll write out the general equation form. This is one way that they can, on the final, we can link back to an old topic. So our response is earn. So earn hat is, what's our slope? Our intercept, sorry. What's the number for the intercept? It's the 14,000. We're looking at this column now, coefficient. Plus, what's our slope? SAT. That's the equation of our line. Anyone have questions on how we got that? Okay. That's our line. So, what is this number out of the symbols that we talked about for the hypothesis test? It is SE of what? E1, right? It's 1.545. So if you got a table, you don't even have to do that calculation. There's the number. What's our t-score? With n minus 2 degrees of freedom. Actually, before I do that, what is our degrees of freedom? 704, right? What is our sample size? Yes. Now, the tricky part, this is definitely something to take note of, is what is S? This is our S sub E. This is our standard deviation, the residuals in this question. What's our t-score? For the hypothesis test? This did the whole hypothesis test for you. What's the t-score and the p-value? What? No. Right, we're looking at this row. So yeah, our t-score is 17.6, our p-value is less than 0.0001. So it did the hypothesis test for you. What you'd see on like your test is you'd get a little like a paragraph, you'd like this, you'd get this picture, it might say do the hypothesis test. All you guys have to do is write the hypotheses and the assumptions. And then you say from the table, t-score is 17.6, p-value is super small, so we reject the null hypothesis. That's all you guys got to do. So you don't even have to do the math. There's no math, it's just writing sentences. Any questions on how I interpreted this table? Because this is important to interpret the table. So S is your standard deviation of the residuals. Do you guys remember what R squared is? R squared is the fraction of variability in Y accounted for by the model. So only 30.7% is accounted for by the model. That's pretty bad. That means, almost 70% is not accounted for by the model. So this is a pretty bad linear regression, right? I mean, this question's basically, it's using SAT score to predict how much money you earn in life. This is basically saying that SAT, at least SAT score, at least by itself, is not a good indicator of how much money someone's gonna make later in life. So yeah. Also, one thing I want to note. So you're given SE, you're given S sub E. You can actually, I don't think you'll have to do this, but you can back solve for S sub X from here. Because remember, it's SE of B1 equals SE, SX, and minus 1. So we have that S standard error is 1.545. SE is 5603. That's big. Over SX square root 705. So you can cross multiply and solve. And you get SX is and you plug that into your calculator, and that's your S sub X. Just so you guys know, are just aware of how you can manipulate. Because S refers to standard deviation of residuals. You just have to know that. What? So S is always referring to S sub E. Yeah, just always. But you can back solve just the default, the data standard deviation. Any questions about this stuff? But so on the test, you will basically get a table that looks just like this, just slightly different. Okay, if you don't have any questions, we're going to go back to chapter 9. So, as in this example right here, one predictor is not that good at predicting how much you earn in life. In real life, we're usually not just going to have one X predicting Y. We're going to have a lot. The example I've been running with in office hours, if after the first test, I did, I plotted your data, well, it'd be categorical, but if I took just your exam 1 score and I use it to predict your final average, that probably wouldn't be that good a predictor, right? Because the next test, you can go up or down or stay the same. If I added in test 2, that'd be a little better. If I add in test 3, I can probably, just using your 3 exam scores, predict what your final average is and be with pretty high accuracy, right? If I know roughly how you're doing on each of the topics and stuff. So sometimes, well, almost all the time, we want more than one predictor. Simple linear regression, as it's called, looks like this, right? But we can add a second predictor, a third one, and we can keep going. I worked with a professor who used 900 predictors. It's more common than not. For something with she was looking at leaves for something about some characteristic of them, and used 900 genes in the leaf to predict something.
What's she right? Did she predict it?
Well, yeah, she made a model. It wasn't linear regression. It was well, it's a whole different type of regression, but it was pretty cool, yeah. But this is the more common scenario. Now, when we have one X and one Y, we have a 2-dimensional graph. I want to do this again, if you're in office hours, don't spoil it. If you have 2 predictors and 1 response, how many dimensions are you in? 3. That's why I'm holding up 3 fingers. Something like it's 1, it's 2, and Y. It looks like this, 3 dimensions. And a line in 3 dimensions, is a line, right? we're living 3 dimensions, it's a line. Once you have 3 predictors, you're in 4 dimensions. 4 dimensions is the last dimension we can kind of visualize. The 4th dimension in real life is time. So basically you need to imagine things growing or shrinking over time, which is weird. But it is true. It's mathematically true. It has been proven that it is impossible to visualize 5 or higher dimensions. So by the time we have 4 predictors, we lose all sense of visualization, which is not necessarily a bad thing. We just have to rely on the math. So once we have a bunch of predictors, we can still plug in numbers into this equation, right? It's just a linear equation with a lot of variables. We just lose sense of visualization, which is okay in the real world. But now that we have multiple predictors, we can run to the issue of predictors being related to each other, right? When we just have the simple linear regression case, this part, obviously X is related to Y. If it's not, then the null hypothesis is true and the slope is 0. But obviously X and Y have to be related in some way. Remember, there can be correlation, but that doesn't mean causation. But they need to be related in some way in order for us to do this. Now, X1 and X2 can be related. X3 and X1 can be related. We can have all these predictors relating to each other. The worst form of predictors relating to each other is called collinearity. This is when 2 or more predictors are linearly related to each other. This is bad, and I'll show you why with an example in a few minutes. Are linearly related to each other. It's the words co and linear with an extra L. Now, if we have something like this, that's good. We want the predictors and our response to be linear related, right? This is a straight enough condition. And we want this to be true for all our predictors. Let's say we just have 2. The thing we do not want is this. This is bad. And the picture on the right, this is called a partial regression plot, which is an optional subchapter, but it's kind of a useful picture. Linearly. There's something I'm looking for on this page. Yeah.
What's the difference between those ground?
The axes.
Oh.
You see, the first 2 have Y on the traditionally Y axis. The one on the right has X1 and X2. So that is bad. That is collinear, a linear relationship between 2 predictors. Also, before I forget, degrees of freedom, it's going to be n minus the number of predictors. Every time you add a variable, you take away degree of freedom. Let me show you. But this is really the gist of collinearity. I'm going to show you in an example how you can find these collinear variables. Any questions on this though? These pictures. Oh, and also, before I forget, we have R squared, right? The fraction of variability in the response accounted for by the model. Now that we have multiple, there is a adjusted R squared. This, it weighs. How do I want to say this? It accounts for the effectiveness of each predictor. So something that's very possible is you have too many predictors. Like maybe I just need your 3 test scores to pretty accurately predict your final grade. Maybe I don't need your quiz scores also. If I added quiz scores in, it actually lower the adjusted R squared because we have too much information. At the end of the day, we don't want too many variables, but we're probably going to need at least a few. This is a very important relationship is adjusted R squared is always less than R squared. Only if they're both 0 or both 100% can they be equal, but basically always adjusted R squared is less than R squared. They're equal only if you have a perfect model or a anti-perfect model. You can't hand calculate adjusted R squared. That's something a computer does. You'll be given it. This R squared is so when we have at least 2 predictors, like on the right, it becomes adjusted R squared. It just doesn't say that. Let's look at this example. So here's an example of a multiple regression plot. This is actually the same example continued. Which variables are intercept? Intercept. So SAT is our first slope. Need percentage is our second slope. So what would the equation of our regression be? Who wants to tell me? Yeah. Mm-hmm. Anyone have questions on? Yeah.
You have to write SAT and percentage need.
You can do X1, X2, but you should define what X1, X2 are, just so we know. Yeah. All right. But that's what the equation looks like. Yeah. Right here, responses earn. So what's our degrees of freedom? What? Yep. What's our sample size? Mm-hmm. Right, yeah, see this? So this R squared is our adjusted R squared now. Because we have multiple predictors. Now this is 35.5. I got to you in just a second. This is 30.7. So by adding need percentage, we've made a better model. It's still not that great a model, but at least it's, like about 5% better. Yeah. This you mean? Well, adjusted R squared is less than R squared. So yeah, this is the adjusted R squared because we have multiple predictors. Well, the real R squared for this would be bigger. Like there'd be another R squared now because there's another, maybe like R squared is like 40%. But we don't use the true R squared once we have multiple predictors, we only talk about the adjusted R squared. The pure R squared is theoretical once we have multiple predictors. So the only one, we know it's just less than the real R squared. Does that make sense? Like, we don't know what the true R squared is. We just know that adjusted R squared is less than that. R squared is like an ideal that we're trying to hit. But this makes a better model. So looking at these p-values, these are all statistically significant. You can do a hypothesis test for the intercept too. We won't do that, but it's kind of just pointless. It's just where you anchor a line at the end of the day, because usually the intercepts don't have meaning. But these small p-values mean that we've rejected the null hypothesis that the slopes are 0. So we conclude that we do have slopes, right? So if one of these was a big value, like if this is like, let's say it was like 0.17, then we'd say we don't need SAT anymore because we'd fail to reject the null hypothesis that the slope is 0. Any questions about that? Okay. Let me show you an example of collinearity. Okay, this was in the textbook. That's a good example. So let's focus on the top one. This is talking about our response is duration of a roller coaster ride. So we have an intercept and our variable is drop. Like, I think it's just how far a drop is on a roller coaster. And we're trying to use the drop to predict the length of time you're on a roller coaster. So we can see that the p-values are significant. R squared is pretty low, right? It's not the best model. So we add a new variable, speed. Now, pay attention to the p-values. Notice how drop went from significant to insignificant once we introduced a statistically significant variable called speed. Also, the drop coefficient was positive here. It's negative here. This is one way of telling that we've found collinear variables. And doesn't it like logically make sense that the farther you go down, the faster you're going to go, right? Because gravity. I mean, really, it'd be like exponential or something. But so this is how we know we found collinear variables. We had something that was significant turn to an insignificant variable when introduced to a new variable. And also, the R squared went up by about 6%. So not only is speed collinear with drop, but it's better than drop. This would actually tell us to remove drop and just have a one variable with speed because the p-value is, 47%. And also the intercept is insignificant now too. That doesn't really matter, but yeah. Yeah.
How they're collinear?
I mean, how they're collinear just has to deal with physics. But like, look at the change in the p-values, right? It goes from significant in the first model to insignificant in the second model, statistically insignificant. And speed, the new variable, is significant. So we found, logically drop and speed are related. And by seeing the change in the p-values and the fact that the coefficients change from positive to negative is how we know they're collinear. You'd need to see both these tables in order to do that. Or a plot of drop and speed. Yeah. Well, that doesn't matter, right? Because like, that doesn't matter, just say alpha is 0.05, right? In this test, we reject. In this test, we reject. Yeah, you don't need to compare the p-values. But I mean, well, the important part is that drop became insignificant. Well, because the p-value is now 47% instead of a fraction of percent. We see they're collinear because we added a new variable that completely, that not only changed the table, but made the previous variable just insignificant. It wiped it off the board. And then you have to think logically to think, okay, there should be a linear relationship between drop and speed. So there's the real life context that's factoring in there too. Someone else have a question? Yeah.
So why drop went from eight?
Because we introduced a collinear variable, speed. That's the answer. Because we introduced speed and it's linearly related to drop. But it's the fact, like the fact that it goes from significant to insignificant is what clues you onto the fact that there's a collinear variable now. And obviously we went from one variable to two variable. So the only option is that it was speed that did it, you know? Yeah.
So for example, if the p-value for drop was like 0.00 like 08, right?
Okay.
For speed speed was still a thing, right? Then both of them would still be significant and there would be no collinear.
Yeah, if in the bottom, if they were both small p-values, then they wouldn't be collinear. Yeah. Everyone see that? So if the 0.46 was like 0.001, if they were still both statistically significant, that would mean that they are not collinear. But it's the fact that speed comes in and just completely negates the usage of drop. That is how you know they're collinear. Yeah. Probably. Adjusted R squared. It probably would, because now we have a useless variable. So removing it would increase the adjusted R squared. Because adjusted R squared penalizes you if you have statistically insignificant variables like drop. So yeah, we would expect our adjusted R squared to go up. But there's no third picture in the textbook, so we don't know. Any other questions on these examples? I think I have one more. So we start with two variables. So this is about where this is for hockey goals. So shots is the number of shots on goal. TOIG is time on ice. Notice how shots and time on ice are both significant. R squared 54%, not horrible, but not great. Just the higher the better, 80% something, 90%, whatever. Here we add a fourth variable, shoot percent. Now, this is what I'd call a good R squared, right? Goes from this to this, yeah. Just because they're small. I mean, let's just say alpha is 0.05. It is true that if like alpha was 0.025, this would be insignificant. But we know the shot, right? 0.002, that's always going to be significant. But you're right, time on ice might not be significant at like alpha value of 0.01. Let's just assume alpha is 0.05, just for great. Yeah. Yes.
So in this scenario,
I'm getting to it. I know what you're about to say. Ice time now has that p-value with the introduction of shoot percent. So it went from small to big. What variable is it collinear with? Alex, you answer me. What variable is it collinear with?
What does it say under the red highlight?
Oh, shoot percent.
Both.
Just one of the two. It's with shot percentage, right? The introduction of shot percentage negated the usage of ice time, right? It turned ice time from a statistically significant variable to an insignificant one. And the reason I know it's just shot percentage is that shots is still significant. And doesn't it make sense that the longer you're on the ice, the more shots you're gonna take, right?
But the same thing you said for shot. Like not shot percentage, but just.
Oh wait, what is shoot? Wait. So they define what there's some difference between shots and shot percentage. Okay. Does it make sense that the more time you're on ice, like you're gonna get more good shots, right? Like the Wayne Gretzky's quote, miss 100% of the shots you don't take. No, because it's still significant. It was not wiped out by the new variable. Maybe logically, but
Yeah,
statistically, no. You just have to look at which variable came in and which variable was kicked out, which is shoot percent came in and it wiped out ice time. And it made a much better value in terms of R squared, a much better model. Yeah.
So follow-up question. If you had that became insignificant. Because
Then let's say this is like, if this was like 0.5 also, then you'd say shoot percentage is collinear with both of them. That's totally possible.
But those two don't need to be collinear with each other.
No, not necessarily. You wouldn't know just from this though. You need more data. Just based on this readout, you wouldn't really know how many things are related to each other. You need pictures. Yeah. All I know is my stat teacher said, don't worry. Like, an intercept is just where you anchor a line at the end of the day. That's why we don't really care about things. Like, you know, what is at x equals 0, or this would be 4 dimensions, right? Because we have at x equals the 0 vector, 0, 0, 0, 0. Our fourth value is -9. Well, do we have -9 goals? Obviously not. So like it means nothing in real life. Yeah. Yeah.
Or
Well, the true colon is if we had graphs, right? If we had a graph and it was ice time and shoot percentage, and we saw a picture that looked like this, that's really how you know. But we don't have those pictures. We just have this table readout. So we have to use only the p-values and the change and the fact that the coefficient went from a positive to a negative. That's also a big indicator. Yeah. It'd be like this. It'd be something exactly like this. Yeah. Yeah. I mean, the graphs, like the thing I drew on the right, is really how you find out. But we don't have any of those pictures. You see this means collinear. You see a random assortment of points, this means not collinear. Yeah. Any other questions on this stuff? It is kind of complicated. It is. Yeah.
Is collinear like?
Yes. Because correlation is the strength of the linear relationship. So that's a good point. You know, collinearity means there's a high correlation between two predictors. Yeah. Yeah.
So the only like the other thing, it's like it's something there or the ratio, just like it asks us to figure out or some other value where that some one of the equations.
Yeah. I mean, like you're asking like what's the point of like this stuff, right?
Yeah.
Well, it's doing the hypothesis test for you. It's doing the regression test for each of the variables. So, you know, yeah. Yeah. You would need the table. You know, you'd go to the bottom where the 95%, you'd go up to the degrees of freedom, 61, and find the T critical. So on the bottom of the table, there's the percentages. So you'd go to You're talking about for part C? Or for part? T ratio is your t-score. That's the thing you calculate at the end of the hypothesis test. So this, for part C, this is your B1 over your SE of B1. T ratio is your T statistic. T critical is from the table. Does that answer your question? Okay. Yeah.
So if uh,
Yes. So, I mean, these are less than 0.001 is like so small that it's gonna be rejected at any alpha value. In general, you would need an alpha value. I agree with you on that. Like, is 0.028 always significant? No. But let's just assume it is just for like the sake of the question. Like alpha is 0.05. But in general, no, you would need, I mean, these ones down here are so small, you're always gonna reject. But in general, yes, you would want a significance level. Yeah, yeah. Okay. There's one more thing I need to teach you for your quiz. As of now, this additional topic, this very brief topic will not be on your final, but you have a question or quiz about it. Page. It's not even on my study guide because it wasn't on the last test. It is these two not nice looking formulas. It'll be written for you on, well, yes, answer is yes. So this top one is the standard error for a mean value. In the parentheses is the Greek letter mu hat sub nu. So it's mu, and this is the Greek letter nu, but it looks like a V. This is called the standard error for an individual value. The big thing I want you guys to notice, these parts are the same in both formulas, but for an individual value, you have an additional standard deviation of the residual squared, which would kind of make sense that one data point has more variance, more variation than a whole bunch of points averaged together. So nu, Greek letter nu. So x nu, yeah, this is x sub nu is how you like say it out loud. It is the particular value that you're focusing on. The equation that we're giving to you on the quiz. Basically, this is for doing what's called confidence intervals for a mean and for a point. I'm gonna go off this page for a second. You'll be given the equation on the quiz anyway. So on this graph, you see in the middle how there's those two green lines around a point. That middle purplish line is the individual value. There's a point at, it's actually focusing on a point at 38 on the x-axis. And those green lines are what's called the confidence interval for that individual value using the bigger equation. The dotted red lines are the confidence interval for the mean value. So these are basically two-dimensional confidence intervals called confidence regions. It's not going to come again. It's going to be on your quiz in a minute. You're just gonna have to, so what you're gonna have to do is plug numbers into one of these formulas. And that's it. But the difference, so actually, let me read you an example. So this, do we want to know the uncertainty in the mean body fat percentage for all men with a waist size of 38 inches? That would use the mean value equation because it says the word mean body fat percentage. 38 would be your X new. For the second one, estimate the uncertainty in the body fat percentage for a particular person. That'd be the bottom one, the individual value. Yeah. Standard deviation of residuals. Yeah. And X new would be 38 for both. Yeah. I just don't want you guys to all get zeros in that question. It's a kind of unrelated topic that, yeah. Well, you'll be given to it in the question. You'll see. In this case, yeah. But yeah. Yeah.
That's square, that's their deviation over the square.
Yes. So the left thing, capital SE, is your standard error of the slope. X bar is, the mean, the X data. S sub E is your standard deviation of the residuals. N is your sample size. Yeah. Some of the regression hypothesis test stuff. And a little bit about multiple regression. Oh, there's one important thing I forgot to say about multiple regression. Definitely put this in your notes. Sorry. Every time you add a predictor, all other coefficients change. Always. The slope and all the other, all the slopes and the intercept. It might be a slight change, it might be a big change, depending on collinearity. But every time you add a predictor, you go from 1 to 2 variables, 2 to 3, 3 to 4, whatever. It will always change all the other coefficients. You can't predict in advance how it'll change it or how significantly it'll change it, but it will change at the least ever so slightly. That's a very important fact. Yeah. Like, so this.
Yeah.
So what? You said go up. I heard up. Anyone else hear up? Thank you.
Well, it's also going down.
Yeah. You don't need to write down. It's gonna be on your quiz. And it's not gonna come up ever again. Yeah. All right.